In the previous recording, I discussed the existence of another property that protons and electrons carry along with their mass, and that property I called electric charge. The reason for that discussion is that it turns out that the property of electric charge is what causes the existence of the force that I demonstrated, the plastic rod attracting little bits of paper that were sitting on my tabletop there. So the simple fact that the pieces of paper jumped around in response to the closeness, the proximity of the plastic rod, even though the plastic rod didn't touch them, clearly indicated the existence of a force. That force, as I pointed out, is unusual in the sense that it acts over a distance between, in this case, the plastic rod and the piece of paper and little bits of paper. The force acted even though the rod and the paper never actually came into physical contact with each other, never actually touched. So I proposed a model that says that the protons and the electrons are the source of the electric force and also apparently respond to an electric force. And so anyway, this physical property I call electric charge. And I also said that whatever this property is, whatever electric charge is and whatever it means, it turns out that protons and electrons, and these are all experimental results, by the way, these are all conclusions from experiment. We concluded that the proton and the electron, all protons and all electrons carry exactly the same amount of electric charge, but we labeled them one positive and the other negative as an indication that the force, the electric force that a proton causes, points in exactly the opposite direction to the direction of the force that an electron would cause. The forces are identical in magnitude, which is why we conclude that the proton and the electron carry the same amount of charge. But as I say, the forces point in opposite directions, and so our explanation for that is to say that the charges that they carry are opposite, and we chose positive and negative to indicate those that oppositeness. Okay, so we have this new property called electric charge. Other than the fact that the protons and electrons carry some, and that apparently it can come into two types, what else can we say about electric charge? That's my next subject. So, properties of electric charge. We have a new force, an electric force. Something is causing that force. What's causing it? Electric charge. What's an electric charge? Well, it's a property that an object can have. What properties does the charge itself have? What properties does this property have? Well, there are a number, and the first one I've already sort of described. It turns out that in our universe, there are exactly two types of charge. No more, no less. You might wonder, what about the neutron that has zero charge? Well, it has that zero charge. Actually, it turns out that the neutron does not have zero charge. What it has is zero net charge. The neutron, you'll learn later in another course, is actually what we call a bound state of an electron and a proton. As I mentioned in the previous recording, when you have, as I mentioned earlier, the proton and the electron carry the same equal amounts of charge, but they carry opposite types. And so when you get a proton and a neutron together, the overall effect is the same as if there was no charge present at all, because anything the positive charge does, any force that the positive charge creates, the negative electron creates the opposite force, and so the net force is going to be zero. The same effect as if there was, in fact, no charge at all. So an object is electrically neutral, not because it doesn't have any charge, but rather because it has the same amount of positive charge as it has negative charge. Okay, so there's that. So there's only two types of electric charge in our universe. No one has ever discovered a third, and we have all sorts of theoretical reasons to believe that there are only two and can only be two types of charge. So there's that. We label them arbitrarily as positive and negative. Again, as you'll see, I mentioned this in the last recording, that this choice of label, positive and negative, to indicate the oppositeness of them was a very poor choice because it leads to endless confusion when you're trying to actually calculate forces, but I'll describe that when we get there. Okay, so there's only two types. Another property, and I just finished saying this, but let me write it down formally. Okay, so the language that we often use is that forces will cancel each other. I emphatically, though, want to say that I want to say emphatically, though, that again, this does not mean that if you get a positively charged object and a negatively charged object together, that they cancel each other and they both vanish into nothingness or anything else like that. That's not at all the case. It is simply the fact that whatever force the one causes, the other one causes an equal and opposite force, so for no net force. And that's how we determine the existence of these objects in the first place, and the existence of electric charge in the first place, was the existence of a force. So if they both create equal and opposite forces, no net force, then effectively no net charge. So but I want to point out a different thing about this. Equal amounts of positive and negative charge cancel, and furthermore, they cancel exactly. It's not an approximate calculation or nearly close or really close or anything else. It's an exact calculation. And it turns out that there's no compelling physical reason why our universe had to come into existence with this particular physical law in place, but it happened to, and so there we are. That's one of the physical laws that our universe happened to get as a result of how the Big Bang went, and so that's our rule book for our universe. That's one of the rules in our rule book. Okay. Okay. Now here comes the biggie. Charge is conserved. You'll remember conservation of energy, conservation of momentum, conservation of angular momentum. When I say that something is conserved, I mean that the total amount of the stuff that you have cannot change. Okay, and conservation of charge means exactly the same thing. Our universe as a whole has a certain amount of positive charge. It has a certain amount of negative charge. And those values are fixed. From the moment our universe came into existence until the moment it disappears down the last black hole, the net charge of the universe will never change by a single coulomb, or by a single electron for that matter. You can move charge around from place to place to place, and we do that all the time. Every time you flip on a light switch, you do that, as we'll learn. But so you can move charge around all you want, no problem there. But you can't. But charge will never simply appear and disappear into nothingness. Okay, it can't disappear into nothingness. It can't appear suddenly from nothingness. Charge is conserved. Okay, and it goes further than that too. In fact, not only is charge conserved, but it is locally conserved. By that I mean that however much charge you have sitting on your desktop, if I have a cup full of protons here, however many protons there are in this cup of double tall non-fat milk cream mocha protons, however many protons there are in here, they will stay here inside the cup. In principle, conservation of charge, they could disappear and then reappear on the other side of the Milky Way. That wouldn't violate conservation of charge, but it turns out, just experimentally, we find it doesn't happen. Okay, and there are good reasons why it doesn't happen. We understand why it doesn't happen, but I want to point out to you it doesn't happen. So you can move, again, you can move charges locally. I love protons, but they don't simply vanish. Okay, so however many charges you have in your circuit, in your diagram, I'm sorry, in your circuit, in your laboratory experiment, whatever it is you have, wherever your charges are, however many charges you have in your battery, how many charges you have in your laptop, whatever it is, there they will stay. They won't simply vanish, okay? So you can kind of count on that. All right. Another thing, another property that matters, very important. Charge is quantized. What does that mean? Maybe you've heard of quantum particles or the quantum of the electromagnetic wave or something like that. Quantized. The word quantum and quantized and quanta and all these other things come from a Latin word or Latin phrase, I should say, meaning how much or how big. Okay, and what this means as a physical matter is that there is a smallest possible amount of electric charge. And in fact, it turns out that that number that I gave you in the previous recording, which is the amount of charge that the proton and the electron both carry, that 1.602 times 10 to the minus 19th coulombs, that numeric value is in fact that smallest possible amount of charge. So another way to say the same thing is that it is impossible for any object in our universe to carry an amount of charge smaller than this elementary value. (1.602 times 10 to the minus 19th coulombs), and the symbol E is often used to represent this smallest possible amount. Personally, however, I prefer Q sub E, and that's the symbol that I will generally use. And the reason for that simply is that there's another very common use for the letter E that frankly is more, well, yeah, there's another use for the letter E that I don't want to confuse this with that other use for the letter E. It's the basis of the exponential function, in case you happen to know what that is. Anyway, so this is the so-called elementary charge. And the subscript E there stands for elementary. It doesn't stand for electron. It so happens that as I think I said a moment ago, the proton and the electron both carry this amount of charge. The proton carries a positive amount of that. The electron carries a negative amount of this. And so there's no particle in our universe that carries less charge than this. It can't happen. Sidebar. This is an aside. For those of you who have ever heard of quarks, you might be raising your hand at this point and saying, hey, what about quarks? Quarks carry just 1/3 of this or 2/3 of this. And yes, you're correct. But two things. One, you know more than is good for you. The second thing is, yes, in fact, quarks do carry an amount of charge smaller than this, but we have never been able to see quarks in isolation. They're always in a bound state, and that bound state always carries this amount of charge. And there's reason to think that quarks cannot exist other than in a bound state, or at least not for any amount of time worth mentioning. And so Yeah, so we don't worry about that. That doesn't really violate this rule. And even if it did, then all I would simply have to say is there is an elementary amount of charge. There is a smallest possible amount of charge, and a quark can carry that much. And then, but quarks are always bound together in three of them. So the elementary, the fundamental, the quantum of charge would be whatever a quark carries. But anyways, end of sidebar. For our purposes for this class, this is the fundamental charge. This is the smallest possible amount of charge. No object can have less charge than this as far as we're concerned in this course. Okay, so that's good. The other thing, though, is yes, this is the elementary amount of charge, but no, on pretty much any scale, this is a very, very tiny number. Okay, and what's going to happen? The next task I'm going to tackle is an understanding of this electric force that we have observed and that we are trying to explain. And this entire charge model is part of explaining the electric force. When I do that, when I tell you what the mathematical expression for the force is and how we calculate that, and then I'm going to talk about the, when the forces are attractive and when they're repulsive, and what other things affect how big the force is, and so on and so on. I'll go through all sorts of things. And in my early examples, I'm going to calculate forces and things regarding just like two electrons, or an electron and a proton, or two protons and one electron, or something. I know there's some very small amounts of charge, but the fact is that most objects that you encounter on a day-to-day basis are made of trillions of trillions of trillions of atoms, and therefore trillions of trillions of trillions of charged particles. And on the scale of something like just a glass of water, the number of charges, and therefore the amount of the total amount of electric charge you have, if you've got a trillion, if you've got a trillion protons, then you've got a trillion to what, 10 to the 9th, and so you've got a charge of 1.602 times 10 to the 10th coulombs total. If you have a trillion protons, that's a lot of protons. Okay. As a practical matter, other than some very artificial textbook examples such as the ones we're going to start with, in reality, we almost never calculate forces on electric charges one particle at a time. We do things in the aggregate, and I will explain how that works and when we do that and how we do that in future lectures. But for now, the viewpoint that I want you to take is that if you have more than 2 or 3 or 4 individual charged particles, that we stop looking at these forces as being between one charged particle at a time with another one charged particle at a time, and instead we start thinking of them as a continuous fluid almost. And in fact, that's not a bad choice. The analogy that I'm trying to draw here is very similar to if you were to ask questions about the forces on the water in a glass of water, or in a swimming pool, or in the ocean, you wouldn't for a moment, even though you know that even in just a glass of water, that it's made of a bunch of H2O molecules, you would never try to calculate what the glass of water, where the water is going to flow to when you pour it out. You would never try to calculate it one water molecule at a time. You treat it as a continuous fluid. It would never even occur to you to deal with the individual water molecules, H2Os. Okay, so you just treat it as a continuous fluid, even though you know that in reality the water is made of individual water atoms or water molecules. Okay, we eventually, when that time comes, we will take the same approach to electric charge. We will stop thinking of them as individual particles, each one containing some amount of charge, but we'll think of it as sort of a continuous charge fluid, or charge distribution, or charge density, something like that. So, but we've got to start where we need to start. So, to my last topic for this recording is I'm going to finally introduce you to the mathematical equation that will allow us to calculate the force that you saw, for example, in the earlier recording between the plastic rod and those little pieces of paper. So let's do that now. I'm going to simply hand you the equation. I'm going to describe its, or at least define the crucial things within it, and then end the recording there. And we'll talk about, and then we'll, in the subsequent lecture, subsequent recording, we'll go through it in detail and along with some examples. Okay. So we have an object made of atoms. The atoms carry protons, the atoms carry electrons. Electrons and protons have their electric charge. Protons have a positive charge. Electrons carry negative charges. So a few more things about what we find. A few more things about what we find. I'm going to pause the recording just for a moment because I want to think about something. Okay, back. So suppose we have, well, let's take the simplest possible case and we'll build our way up slowly from there. The simplest atom that I can think of is a hydrogen atom. Now, perhaps you know, a hydrogen atom, well, like all atoms, it has a nucleus, and then orbiting it is the same number of electrons that are in the nucleus itself. And the reason for that, by the way, will become clear actually when I write this thing down. Hydrogen atom, as it happens, in the ordinary hydrogen atom, its nucleus is comprised of just one single proton, not even any neutrons. Right? So the nucleus is a single proton, ergo there is only one electron that is orbiting it. So we have the nucleus of hydrogen, and somewhere nearby it is the electron. The sizes of the symbols that I'm using here have no real meaning. If you want to insist on a meaning, you can say that you can interpret it as that the proton and the electron, I drew them the same size, indicating they carry the same amount of charge, whatever. So then the question is, let's ask, what force does the proton exert on the electron? Well, first off, I hinted earlier that the force is either attractive or repulsive. I also, well, let's let me just do it like that. To start with, let's think about the magnitude of the force first. The magnitude of the force. I hope it makes sense that the more charge that the objects carry, bigger the force is that they are going to create. After all, it is the electric charge that causes the electric force to even exist. So the more charge you have, the bigger the magnitude of the force should be. And in fact, I'm going to I just changed my mind. I'm going to withdraw this. Let's not call it a hydrogen atom. Let's just say I have two particles here. One's negatively charged. So forget the whole hydrogen atom thing. Forget it. This is just a negatively charged particle. This is a positively charged particle. They could be anything. They could be bricks, right? Okay, so yeah, forget the whole atom thing. All right, so then the question is, what is the force on Q1 due to Q2? Okay, and so I'll call that force F. Now, first of all, let me do a proportionality here. First of all, I hope it makes sense that the bigger the charges are, I was just explaining this, the bigger the charges are, the bigger the resulting electric force should be. So that, in other words, mathematically, that means that the force is proportional to Q1, and it is proportional to Q2 as well. You can increase either one of them or both. and you'll get a bigger force. Second of all, I would suggest to you that the strength, the magnitude of this electric force is going to depend upon how far apart the two charges are from each other. Let me make that reasonable by saying, well, if the two charges are this close to each other, they're that close to each other, okay, the force that they exert on each other will have a certain strength. But on the other hand, if one is here and the other one is in Australia, then oh, by the way, where's here right now? Right at the moment, I'm in Bellevue, Washington, in the United States, near Seattle. So if the other charge went to Australia or was in Australia, I hope it's reasonable that the force that it would experience would be a lot weaker than the force that when the two charges are this close to each other, okay, a few centimeters apart. And so in other words, as the distance between them gets bigger, the force between them gets smaller. In short, if I label the distance between them, call it r, for reasons that will become clear later, then the magnitude of the force should be inversely proportional to the distance between the two charges. It turns out that, in fact, the force is inversely proportional to the distance, but not just to r, but rather it's inversely proportional to r squared. I'm not going to try to prove that other than to invoke experimental fact. This is what we find experimentally is the case. Okay. Why it's 1 over r squared, maybe we'll get into that, maybe we won't, but the fact is that's what it turns out to be. Okay. And then you can kind of think about other possible things, but there won't be anything else. And so this ends up being it. With one subtlety, we'll discuss it later. In any case, so mathematically then, what do we have? So we have, well, physically we have that the magnitude of the force that Q1 experiences due to the presence of Q2, that force depends on how big Q1 is. It also depends on how big Q2 is. It depends on the square of the distance between the two charges. As a mathematical matter, if something, in this case F, is proportional to multiple other things, then F is proportional to the product of those other things. And so that means the magnitude of F is proportional to the product of the two charges divided by the square of the distance between those two charged. By the way, terminology. It's sloppy language, but it's very common. Technically, what I have two particles here, and the two particles carry lots of properties. They carry mass, they carry volume, they carry temperature, they carry various other things. They carry charge. So charge is one of their properties. So what I should be saying is, what is the force on particle number 1 due to particle number 2, given that particle 1 has this amount of charge that I called Q1, particle 2 has some amount of charge that I called Q2. The sloppy language that we almost universally use is, if I'm only interested in the electric force, that I often will simply talk about the charge Q1 and the charge Q2, rather than what I should say is the charge on particle 1 and the charge on particle 2. So that's sloppy language, but as I say, extraordinarily common. You'll end up doing it too. I'll do it all the time, so that's what it is. So I'm getting that out of the way. Okay. Right. The only thing we need now, again, invoking mathematical rules of the game, that the way you turn a proportionality, F is proportional to this thing, the way you turn a proportionality into an equality so that I can actually calculate numbers is you have to multiply the right-hand side by a so-called proportionality constant. So we will do that. And we'll just use a nice simple symbol k, lowercase k. And we are almost done. The reason we're not quite done is because we are talking about a force, and like all forces, this electric force is a vector, so we need to worry about the direction as well. So coming back to this diagram, so I'm going to erase some of this stuff here so I can diagram this. Actually, you know what? I think I'll save that discussion for the beginning of the next lecture. This one's gone on long enough. Next recording, please.